Hey everybody. I wanted to give you a heads up that we're going to engage now in the so-called strategy pattern. I would consider strategy pattern to be one of the most powerful patterns available to us as object-oriented programmers. As you may recall from the introduction on patterns, a pattern typically solves a well understood problem. It has a name, and it gives us a mechanism upon which we can kind of hang our hats. It gives us a nomenclature that we can use to discuss how we can design our object oriented systems. The centerpiece of the pattern, at least in Java, is the interface. The interface in Java is typically devoid of any implementation. It contains only a specification for methods, no implementation for the methods, and certainly you can implement multiple interfaces. The only exception to the rule about lack of implementation in Java, anyway, is that you get static constants, and those constants are embedded inside of the interface, and they cannot be altered. They are implicitly final. The basic design principle that I use when I design an interface for a framework is I want to curate the simplest possible interface. So what this is essentially a statement about my personal preference in design, and that is because if you have a very simple specification that you can disseminate widely in your team, everyone can program to that specification, and it makes system integration later on a lot easier. It also makes outsourcing the various components that will plug into the interface a lot easier. And later on, because you have a common interface, creating new graphic user interface skins on top of the components that implement the interface is relatively simple. And so if somebody said, well, today we're going to program in Swing, and tomorrow we'll use AWT, and the next day we'll use SWT, and maybe then we'll use mobile, and then we'll do something else, at least the interfaces that have been implemented will not have changed, and the components which implement those interfaces will not have changed. And so this allows for what I would call good component software development, essentially interchangeable parts. The interchangeable parts theme is probably the one that most characterizes the dawn of the Industrial Revolution. It was Eli Whitney who went in front of Congress with many guns, disassembled them in front of Congress, and then reassembled them in order to be able to get fully functional guns, changing pieces in between. And this impressed Congress to the point where he was able to get a lot of gun manufacturing contracts. Having interchangeable parts in software in general means component software development. When you look at something like the impact or inertia that has accompanied an interface design, I cite common interfaces. Here's one called Runnable. Anything that implements the Runnable interface has a run method, and that run method can have arbitrary complexity. There are, in my project, 286 classes which implement the Runnable interface. Now, if one were to change the Runnable interface, I would have to visit all 286 of those classes before I could get a clean compile again. And certainly that would be more work than I would care to take on. Similarly, I have a framework for doing image processing, and that framework revolves around the so-called image processor interface. The image processor interface, let's see if we can do this. Here we go. The image processor interface has a garbage in, garbage out arrangement. Images come in, they get processed with an arbitrarily complicated system, and then the images come back out. I have 104 classes which implement the image processor interface. So when you have an interface, your basic goal is to program to the interface. And with one interface, you can have many implementations. And each one of these implementations is said to be a concrete class. And so this allows us to do what I would call a maximization of cohesion with a minimization of coupling. And this brings to mind one of the basic metrics of object-oriented complexity, and that is, I would call it, the inter-object associations that you may obtain. That is, if one object knows about the other object and maybe 10 or 20 of its friends, then in effect you have an enormous amount of interdependency. And that interdependency creates a certain metric of complexity that makes things fragile. It means it's harder and harder to change one thing without breaking something else. Here is a UML depiction of an interface, and it allows you to choose any one of a number of different algorithms. And certainly you could use algorithms or behaviors or operators or whatever you like. In some context, you will have a instance of something that will choose one of several implementations of the interface. And that is your strategy design pattern. So what we have here in the diamond is composition, and the client makes reference to some context and then chooses implementations of the interface. So it's very good for operators, very good for selecting multiple algorithms, great for providing frameworks if you can find a simple interface that a lot of operators implement. And in effect, if you're using the interface, what you have is polymorphism. And so with polymorphism, it means poly means many, morphism means shapes. As it happens, it also enables us to promote component software development, and it promotes code reuse. General lack of code reuse has characterized software engineering for many years. By being able to promote code reuse, we essentially address one of the big problems in software engineering. So you've got to identify behavior, and then you have to find the simplest interface which can be used to provide a specification for that behavior. And I'll give you a few examples of that with some real-world code. One of the problems I have with C++ is that it allows multiple inheritance. But if you go to Objective-C on the iPad, it does not. And similarly, if you go to Java in the sense of multiple inheritance of implementation, it also does not. So you can have multiple inheritance of specification in the form of implementing multiple interfaces, but since the interfaces contain no implementation of any methods, you basically have a dead end in Java. You can't have diamond inheritance, you can't have multiple inheritance, and so in effect, when you're dealing with inheritance, you're dealing with an AKO or a kind of hierarchy. And so this means you have a directed acyclic graph, which essentially depicts all of the Java classes as leaves inside of a tree. So it's very good if you want to have different classes with different behavior. It also enables you to avoid subclassing because it favors what I call composition, that is HASA versus ISA. So what we were looking for with the context is a kind of, I'll call it, runtime selection of the implementation. Someone has to decide which operator you're going to be using. And we're going to be building interchangeable parts. So our concrete strategy is going to be a function of our context. So someone is going to say, well, I'd like to do an operation involving two numbers. And then you could say, well, we'll define operators with two arguments, and then we can implement them any one of a number of ways: division, multiplication, subtraction, whatever we like. Here's in a robotic example. We have behavior for the robot, and the strategy is that robots should be able to move. They move themselves. So we have a behavior in the robot, And then the question is, what kind of behavior do we want the robot to exhibit? So then we can have implementations of the behavior interface, and we could have aggressive robots or defensive robots or normal behaving robots. And in fact, in the world of a simulation or a game, that might be very interesting to have different robots with different behaviors, because then we can watch as they interact with one another. And now what I would do is break out into basic examples in Java that would allow you to see the strategy pattern in action. Thank you.